According to the 1999 National Electrical Code, there is no specific prohibition against running a grounding electrode conductor, commonly referred to as a GEC, in an attic space that is inaccessible to humans. However, several important considerations should be taken into account to ensure a safe and compliant installation. Firstly, the GEC must be installed in accordance with the manufacturer's instructions. These instructions provide specific guidelines regarding the proper handling, termination, and support of the conductor. Ignoring these instructions could lead to improper installation, potentially compromising the effectiveness of the grounding system. Secondly, the GEC must be secured in a workmanlike manner. While the 1999 National Electrical Code does not explicitly define workmanlike manner, it generally implies that the installation should be neat, professional, and in accordance with accepted industry practices. This includes properly supporting the conductor to prevent strain or damage. In the specific scenario of running a GEC through an inaccessible attic space to connect to the water service at the front of the residence, it's crucial to address several key aspects. Firstly, ensure proper securing at entry and exit points. The GEC should be securely fastened at the point where it enters the attic space and again at the point where it exits the attic space to connect to the water pipe. This prevents the conductor from moving or becoming damaged over time due to vibrations or other factors. Acceptable methods for securing the GEC include using appropriate clamps, straps, or other listed hardware designed for this purpose. Secondly, protect from physical damage. It is important to carefully inspect the attic space for any sharp edges, nails, screws, or other potential hazards that could damage the GEC insulation. The conductor should be routed in a way that avoids contact with these hazards. If necessary, use protective sleeves or conduit to shield the GEC from potential damage. Thirdly, consider accessibility for future inspection. While the attic space may be currently inaccessible to humans, it's important to consider the possibility that access may be required in the future for inspection or maintenance purposes. Install the GEC in a way that does not obstruct access to other equipment or wiring in the attic. Also, ensure that the GEC is readily identifiable as a grounding conductor. It's important to note that the National Electrical Code is updated regularly to reflect advancements in technology and safety practices. The 1999 National Electrical Code has been superseded by subsequent editions, including the 2002, 2005, 2008, 2011, 2014, 2017, 2020, and the current 2023 National Electrical Code. It is essential to consult the latest edition of the National Electrical Code for the most up-to-date requirements. Significant changes may have been introduced in later editions that could affect the installation of grounding electrode conductors. Changes in the National Electrical Code can cover a wide range of aspects related to grounding electrode conductors. These aspects include, but are not limited to, firstly, conductor sizing. The required size of the GEC may have changed based on the size of the service entrance conductors. Consult the appropriate tables in the current National Electrical Code to determine the correct conductor size. Secondly, acceptable grounding electrodes. The National Electrical Code specifies which types of electrodes are permitted for grounding purposes. These typically include metal water pipes, metal frames of buildings, concrete encased electrodes, and ground rings. The specific requirements for each type of electrode may have been revised in subsequent editions of the National Electrical Code. Thirdly, bonding requirements. Bonding refers to the connection of various metallic parts of the electrical system to ensure electrical continuity and minimize the risk of shock hazards. The National Electrical Code contains detailed requirements for bonding different components such as metal water pipes, gas pipes, and equipment enclosures. Fourthly, installation methods. The National Electrical Code specifies acceptable methods for installing GEC, including requirements for protection from physical damage, securing and supporting the conductor, and making proper connections. It is essential to follow these installation requirements to ensure a safe and effective grounding system. To summarize, while the 1999 National Electrical Code does not explicitly prohibit running a GEC in an inaccessible attic space, it's crucial to adhere to the manufacturer's instructions, secure the conductor in a workmanlike manner, and protect it from physical damage. Furthermore, always consult the latest edition of the National Electrical Code to ensure compliance with current regulations, as significant changes may have been introduced since 1999. Understanding grounding electrode conductors is essential for electrical safety. The grounding electrode conductor, also known as the GEC, serves as the critical link between the electrical system and the earth. It provides a low impedance path for fault current to flow back to the source, facilitating the operation of overcurrent protective devices like circuit breakers or fuses. This process helps to quickly clear ground faults, minimizing the risk of electrical shock and fire hazards. The importance of a properly installed GEC cannot be overstated. A faulty or inadequate grounding system can have serious consequences, potentially leading to electrical shocks, equipment damage, and even fires. It is crucial to adhere to all applicable codes and standards when installing or modifying a grounding system. There are several key components involved in a typical grounding system. These components include the grounding electrode, the grounding electrode conductor, and the equipment grounding conductor. The grounding electrode is a conductive object that is buried in the earth and provides a direct connection to ground. Acceptable grounding electrodes include metal water pipes, metal frames of buildings, concrete encased electrodes, and ground rings. The grounding electrode conductor connects the grounding electrode to the electrical system's grounded conductor, typically at the service entrance. The equipment grounding conductor provides a path for fault current to flow from equipment enclosures back to the source, helping to ensure that metal parts of electrical equipment are at ground potential. Selecting the right size of grounding electrode conductor is critical for safety and performance. The size of the GEC is determined by the size of the service entrance conductors. The National Electrical Code provides tables that specify the minimum required size of the GEC based on the size of the service entrance conductors. It is important to consult these tables to ensure that the GEC is adequately sized to handle potential fault currents. Different types of grounding electrodes are available, each with its own advantages and disadvantages. Metal water pipes are a commonly used grounding electrode, but they must meet certain requirements to be acceptable. For example, the water pipe must be in direct contact with the earth for at least 10 feet. Metal frames of buildings can also be used as grounding electrodes, provided that they are effectively grounded. Concrete encased electrodes, also known as UFA grounds, are typically installed during the construction of a building. They consist of a length of bare copper conductor encased in concrete. Ground rings are another type of grounding electrode that is installed around the perimeter of a building. Proper installation of the grounding electrode is essential for ensuring its effectiveness. The grounding electrode should be installed in accordance with the manufacturer's instructions and all applicable codes and standards. The electrode should be buried deep enough to ensure good contact with the earth, and it should be protected from physical damage. The grounding electrode conductor should be securely connected to the grounding electrode using appropriate connectors. Bonding is another important aspect of grounding. Bonding involves connecting various metallic parts of the electrical system together to create a low impedance path for fault current. This helps to minimize the risk of electrical shock and fire hazards. The National Electrical Code contains detailed requirements for bonding different components, such as metal water pipes, gas pipes, and equipment enclosures. Regular inspection and maintenance of the grounding system are essential for ensuring its continued effectiveness. The grounding electrode and grounding electrode conductor should be inspected periodically for signs of corrosion or damage. The connections should be checked to ensure that they are tight and secure. Any problems with the grounding system should be addressed promptly by a qualified electrician. Common grounding mistakes to avoid include using an undersized grounding electrode conductor, improperly connecting the grounding electrode conductor to the grounding electrode, and failing to bond metallic parts of the electrical system properly. These mistakes can compromise the effectiveness of the grounding system and increase the risk of electrical shock and fire hazards. Grounding and bonding are critical for electrical safety. A properly installed and maintained grounding system helps to protect people and property from the hazards of electricity. It is essential to follow all applicable codes and standards when installing or modifying a grounding system. If you are not comfortable working with electricity, it is best to hire a qualified electrician to perform the work. Staying up to date with National Electrical Code changes related to grounding is essential for electrical professionals. The National Electrical Code is updated every 3 years, and each new edition may include significant changes to the requirements for grounding and bonding. It is important to stay informed about these changes to ensure that your work is compliant with the latest regulations. Resources for learning more about grounding and bonding include the National Electrical Code, electrical training courses, and publications from professional organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the International Association of Electrical Inspectors, or IE. These resources can provide valuable information and guidance on proper grounding and bonding practices. Grounding electrode conductors play a vital role in electrical safety by providing a low impedance path for fault current to flow back to the source. A properly installed and maintained grounding system helps to protect people and property from the hazards of electricity. It is essential to follow all applicable codes and standards when installing or modifying a grounding system, and to stay up to date with the latest National Electrical Code changes. Consulting with a qualified electrician is recommended for any electrical work, especially when dealing with grounding systems, to ensure safety and compliance. Proper grounding is not just a code requirement, it's a life safety issue. By understanding the principles of grounding and following best practices, electrical professionals can help to create safer electrical systems for everyone. In addition to the specific requirements for running a GEC in an attic space, it's also important to consider the overall design of the grounding system. The grounding system should be designed to effectively protect the electrical system and equipment from ground faults. This includes selecting the appropriate grounding electrodes, sizing the grounding electrode conductor correctly, and ensuring that all metallic parts of the electrical system are properly bonded. The grounding system should also be designed to minimize the risk of electrical noise and interference. Electrical noise can cause problems with sensitive electronic equipment, such as computers and audio equipment. Proper grounding techniques can help to reduce electrical noise and improve the performance of electronic equipment. When designing a grounding system, it's important to consider the specific characteristics of the site. This includes the soil conditions, the presence of underground utilities, and the type of electrical equipment being used. The grounding system should be designed to address these specific characteristics and provide effective grounding protection. It's also important to consider the future needs of the electrical system when designing the grounding system. The grounding system should be designed to accommodate future expansion or modifications to the electrical system. This will help to ensure that the grounding system remains effective and compliant with applicable codes and standards. Grounding is a complex and critical aspect of electrical safety. It's important to have a thorough understanding of grounding principles and best practices to ensure the safety and reliability of electrical systems. Consulting with a qualified electrical engineer or electrician is recommended for any complex grounding system design or installation. Remember, a properly designed and installed grounding system is essential for protecting people and property from the hazards of electricity. Taking the time to do it right is always worth the effort. The information provided here is for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrician or electrical engineer for specific advice related to your situation. Electrical codes and regulations can vary depending on your location, so it's important to be aware of the specific requirements in your area.